All right, part two of homework 4. We are going to be writing code to demonstrate that with explicit differentiation, simulating the temperature profile of a bar with length 20 meters, thermal density, diffusivity 1 meter squared per second, spatial increment of 1 meter, and that will limit. We need to show that will limit the time step, your derivative time to 0.5 seconds. So we will get right on into that. We pull up again, like previously. Both these screens are the same thing, so you can see what's going on both. And then I will be using my tablet to write. So let's pull up our pad here. This is all the last step, and then these are just a little bit better notes I took on it, so we can explain. This is our bar here. Again, the left side of the bar is 50 degrees Celsius. The right side of the bar is 80 degrees Celsius, and there is no heat generation inside of the bar. So we can rewrite the equation that we derived last part again here. So the second partial derivative of the temperature over the area. And then since there's no heat generation, we can ignore the heat generation over K proportion. So then we'll just be left with 1 over alpha the thermal diffusivity times the partial derivative of temperature over partial derivative of time. And then we can rewrite that as alpha partial derivative of temperature or partial derivative of time. Perfect, just like that. Now, in order to code this out, we need to break down these partial derivatives in terms of explicit differentiation. And the way that we can do that is by modeling or showing how it changes based on the position inside of the bar with respect to time. So some units that we can use to do this, we can use a position unit, J, and then you can have J is equal to 1, 2, 3. It doesn't matter, it's just a counting unit. And then for time, we can use N. So that would just be J is equal to dx and N is equal to dt. So we'll start with the hard one first. There's second derivative here, or second partial derivative. The first thing we can do here is we can start with the temperature. Oh, that's too big. Can you see all this? Okay, good. The temperature at J minus 1, at J plus 1 minus the temperature at J all over dx minus temperature at Jn minus the temperature at J minus n, or J minus 1, n over dx, and then all of this is over dx. Now, if we look at the bar here, I can see I already laid this out a little bit. J, and then 1 up from J is J plus 1, and 1 behind J is J minus 1. So that's where those are numbers. That's where those are coming from. Then we can rewrite this as here. That's gonna be a delta x squared, and then that's going to simplify down to t over j plus 1 n minus 2 tj and then minus t j minus 1. n. Perfect. Now for the partial derivative of temperature over partial derivative of time, it's going to leave us with, this one's much easier. It's going to be j n plus 1 j n all over, since basically I want to specify why we're going in the n plus 1 direction and not the n minus 1 direction there, because this is the graph we're trying to solve here. Nope, not that. We want it to be linear, but the way it starts out, it's kind of going to be a little exponent here, and we're trying, say we're here, we want to know what it's going to be up here. So that's why we want to know the plus n direction. So that's why it's in the plus n direction, and then that's going to be delta t. Now we can combine these with our equation up here. Just put everything together. Let me make sure I started recording. Okay, I did. Whew, scared me. All right, so we can combine these. So we're going to be left with alpha, this whole term here. So it's going to be t j plus 1 minus n times n minus t n minus t j minus 1 n all over delta x squared. It's going to be equal to t to the j n plus 1 minus t j n all over delta t. Now we can pull out the delta, or the change in x and the change in time. So that will leave us with, it's going to be alpha dt over dx squared. And then this term we are going to call r. This is going to be r. Just for simplicity's sake, for when we go to code. So when we solve for this, we can actually combine these since they're all the same. So that'll leave us with tj n plus 1 is equal to, and then this is all going to distribute to all these. So it's going to be r t j plus 1 n minus r, or I'm sorry, 1 minus 2 r t j n, then minus t j minus 1 and, oh, I forgot another, r t j minus 1 and so that is what we're going to code out. Right now. Let me check to make sure that this is right before moving forward. I will be right back. Okay, I made a little algebraical issue here. I didn't account for the multiplying and dividing. These are actually going to be positives here instead of negatives. But other than that, everything checks out perfectly. So let's go get on Python. All right, part two. We're going to be looking at the coding. So first part here, we imported NumPy as NP, and then from Plotly subplots, we're going to import the plots. From the homework guidelines, our alpha value, which is the thermal diffusivity is going to be 1 meter squared per second. Our time step is 0.5 seconds. Our dx, the distance step, is 1 meter. From our differentiation on paper here, r, which is alpha dt over dx squared, that's what r is, so we imported that as well. Our temperature for the room is 20 degrees. The temperature on the left side of the bar is 50. The temperature on the right side of the bar is 80. And then the length of the bar end is 20. And then the x value here, that needs to be the same as everything else. So that's going to be n. So that's what all those values are. And then we'll just go ahead and look at this one more time just to show you. Length of bar 20, thermal diffusivity, which is alpha 1. And then spatial increment 1, and then time step 0.5. So 1, 1.5, and then 20. So that's what that is. First step we need to do here is to define the temperature. So the temperature, that's going to be equal to the full, and then this needs to match our shape like. So n, and then room temperature here, and then to define our bounds here, so since we're going from the left to the right, so the temperature of the left side is going to be equal to temperature 1, temperature 0, and temperature on the right side is going to be equal to temperature minus 1. Gosh, I always do that. And then the next part we need to do is we need to create a for loop here so we can plug in what we just derived. For going from 1, and then we're going to say 400. I think that should be enough points. And then we need to plug in our equation here that we just derived. Right here. Here, actually, let me fix this because it should be R. This should be J. I don't know why it's R. There we go. Alright. We plug this in. Now when we plug this in, we're not plugging in J and n plus 1. We're plugging in points of the array we just created. So like, for example, this one will be 2 and 0, and this one will be 1 and 1 and 1 and 0. So let's plug that in. So for this is going to be 1 and negative 1. Which is going to be equal to R, if I remember correctly. Again, this is what I'm looking at down here. What you're seeing here is what I'm seeing on my screen. So this is what I'm referencing. So it's going to be R times T. This is going to be 2. And then that's going to be plus 1 minus 2 times R. It's not capital. That's going to be times T to the T times 1 negative. That's just 1. And then this is going to be plus R times T to the negative 1. Alright. Now let me check and see if these are the right array numbers. I always get these messed up, so I just want to make sure that these are the correct ones. Alright, so I did mess up these last two arrays. It's supposed to be 1 and negative 1 and negative 2. Just because this is the negative 1 value for n, and then this is the 0 value for this, and the negative 2 value for that. So that's why I messed those up. So the next part here is we need to do a little index here. So if basically what we're doing is we don't want 400 points. Let's say we only want 25 points. Now if we're saying if I divided by 25 is not equal to 0, which is the remainder, then we're not going to use those points. So basically we're just checking that the remainder is 0 for these and that we can in fact use them in the graph. And before let's actually add the graph up here. So from I always forget how to do this, and we do it in every homework. It drives me absolutely crazy. So let's so we want to import a scatter. I know that. Let me go reference how to do this again. This drives me crazy. So we need to import a subplot here. We need to add a scatter plot. Our x axis is going to be our variable x, and our y-axis is going to be our variable temperature. The mode we're going to have is lines because we want a nice line graph. And then our name, we can name this 0, just doesn't really matter. Why don't you like this? And then we can copy and paste this down here. And then we need to rename this. We can just rename this. That. It doesn't like this. Why doesn't it like it? Well, first thing we need to do is add that there, and then I think this is wrong because we need this, some parentheses. This needs to be F, and then it doesn't really matter what the name is. Make sure everything is cool still. Where do you like this? And then we need to update. I think it's an update scatter. No, I think it's update. Layout. Height. We want to. We'll do width first. Like we're supposed to anyway. Width, we're gonna make 1,000. Height, we're gonna make 1,000. And then template, we're just gonna make this dark because it's on a dark background anyway. And then I can't spell, that would be the reason. Holy error code. My life would be a lot easier if I learned how to spell words. That's wrong. Oh, there you go. I just said wrong. Alright. So here is our graph, or our graphs for the temperature and the time as it changes. And you can see our linear graph is 187.5. That's right here. Now let's just change the time step by 0.01. That's it, 0.01. Let's see what happens. Maybe not 0.01. Let's try 0.08 or 0.05. There we go. We start to get a little more wobbly. You can see that it starts to misbehave. And then let's just jump to 0.51. So let's do a big jump. Look at that. That is absolutely nowhere near linear, nowhere near where we want it to be. So that proves that the limits the maximum time step to 0.05. So in the next part, we'll perform a von Neumann stability analysis to show theoretically the limit of stability on the explicit differentiating scheme used in part 2. All right, thank you very much.